Today we're going to be starting to look at an application of this arc length stuff and angles that we've been talking about. This is section 4.1 in your book, and we're going to be talking about angular speed and linear motion. So we're connecting angular speed, things like radians per minute, into a linear speed, like how fast you're going in miles per hour. So one of the things we'll be able to answer, one of the questions we'll be able to answer at the end of this will be, we have a truck wheel with a diameter of 36 inches. It's rotating at 630 RPMs. Remember, RPMs means revolutions per minute. And we want to find the truck's speed in miles per hour, just knowing that these 36-inch wheels are going at 630 RPMs. So we will be able to do that. So we're going to start by just highlighting, and it would be important to take some notes today, highlighting there's really three different kinds of speeds, and we're going to talk about how they're related as well. So the first one we will talk about is rotational speed. And rotational speed is a real simple concept. It's just thinking about that if I have a ray going around, so when we do circular motion, we're going to think in these terms. So remember, I'm going to think about spinning around, and I'm following a ray, and it's a lot like this air traffic controller over here, or like if you've seen it in movies or whatever, that ray spinning around and around. So the thing about rotational speed that we want to keep in mind is that it does not matter where I am along this ray, that as I go, every point along the ray has the same rotational speed. How many times around are they going every minute? And rotational speed is going to be measured in RPMs, or revolutions per minute. We're really going to take close watch of the units throughout this unit. So we have rotational speed. How many times are we going around this circle every minute? We also will be then talking about angular speed. We can use the variable W to represent angular speed. And it's just describing how fast the angle is changing. How fast is theta changing? Now, if we go back to this idea of this ray going around, if we think about it, the angle theta is inside here. So the angle theta would be the same angle for all of these points along the ray. So the angular speed, whatever the angular speed is at one point along that ray, it's going to be the same throughout. The other thing we're going to keep in mind is that each revolution, every time I go around one full time, I've gone the equivalent of an angle of 2 pi radians. That's going to help us keep in mind the fact that we have one revolution is equal to 2 pi radians. That's going to be a conversion rate that we are going to use as we go from one type of speed to another. Every time I go around one revolution, my angle is changing by 2 pi radians. Next, have you ever heard of the game Crack the Whip? Here's a picture of it. It's typically on ice skates, although you could just be, in regular shoes or roller skates or something. It's more fun on skates of some kind. Well, the whole concept is you have a group of people linking arms, and then you just go in a circle. And if you can imagine what's happening to the person at the end, I actually used to play this game when I was young and growing up in northern Minnesota on the outdoor rinks. We would play Crack the Whip, and whoever's on the end, they are just zipping around to keep up. Whereas whereas the person in the middle, they're just going around a little bit. So this idea of crack the whip will help us to understand the next speed, which is linear speed. So our linear speed is our speed at a specific point. So we have to identify a specific distance from the center, because if we go back to our picture of our crack the whip, the person here in the center, although they're both in the person comparing to the person on the outside, although they both go around one revolution, this person in the center is going a lot slower because they don't have much distance to cover, whereas the person on the outside, they really have to go fast because they have a lot of distance to travel in the same amount of time. So in order to determine a linear speed, you have to pick a specific point along the ray. And then this linear speed is describing how fast that specific point travels their distance, depending on how far away they are. So the further you are from the center, the greater your linear speed. So one way to kind of get a feeling for this is thinking that every point along the ray must make the same revolution in the same amount of time in order to keep up. So the person on the end is going much faster. Now the thing that naturally falls from linear speed is, once we know linear speed, we can figure out a distance traveled. And so we can just calculate that distance knowing how much time they've been going. Next, I'm going to give you a moment. I'm going to pause it right now and give you a moment to copy down this speed chart, and then we'll talk about it. Okay, so the speed chart is a good way to see how these different speeds are all related to one another. And starting at the top, we have rotational speed. And again, we're going to keep those units in mind. Our units are going to really help us decide which type of speed we're talking about. So my rotational speed is how many revolutions for some amount of time. Normally, it's called RPMs, revolutions per minute. Once I know a rotational speed, then I can naturally progress down to an angular speed. And the unit is associated with angular speed is how many radians for some kind of time, like radians per minute, radians per hour. That tells us how quickly that angle is changing. Once we know angular speed, then we can naturally, once we determine a radius, we can then convert that radian to a distance. And so I can go from angular speed to linear speed, which is some kind of distance over time, like feet per minute, or maybe miles per hour, our typical speed that we're used to working with. And once I know then the linear speed, I can go ahead and just multiply it by time to figure out what distance has been traveled. But it's really the interaction of these three speeds that I want you to be familiar with. Notice that I have arrows going up the chart. So for example, if I'm given a linear speed and want to find how many RPMs it is, I'm going to have to get there by first finding my angular speed and then working my way up the chart. Now the key, in my opinion, for this speed chart is to know which unit conversions you're going to use in between. So in other words, to go from rotational speed to angular speed or vice versa, we're basically exchanging revolutions for radians. So my exchange rate, I'm going to go in one revolution, I'm going to do 2 pi radians. we're going to use that whole factor label method to decide, do I want revolutions on the top or do I want to cancel it and put it on the bottom? Now, from angular speed to linear speed, this is where we're really going to be relying on our definition understanding of what a radian is. Because I want to go from having a radian in my unit to making it a distance. Well, if we think about that, whenever I have an angle go 1 radian, if my angle is 1 radian in size, that means that I've covered whatever the length of the radius is. So in my conversion rate here, 1 radian is saying I've covered the equivalent of 1 radius along the arc, whatever distance you're choosing to be away from the center. And again, we're going to use factor label to decide how I'm going to write that conversion rate. All right, let's look at one example of how this all works. Going back to that example from the very beginning, we have a truck wheel with a diameter of 36 inches, rotating at 630 RPMs. We want to find the speed of the truck in miles per hour. So first of all, we want to think about what kind of speed am I starting with? Where am I on the speed chart? And I look at my units and I have 630 revolutions per minute. So that tells me that I am going to be in rotational speed at the top of the chart. Okay. And I look at what kind of units I want my answer to be, and I want my answer to be in miles per hour. So I'm just going to put my answer way out here so my units can tell me when I'm ready to find my answer. And I want to convert revolutions per minute to miles per hour. Now if we go and look back at our speed chart, to go from rotational speed down to a linear speed, I'm first going to have to go through angular speed. So I'm going to go ahead and start setting up my conversions here. And I don't know why I always put a box around it. Just a bad habit, I guess. So my conversion rate from rotational speed to angular speed is the fact that every time I go around 1 revolution, my angle has changed 2 pi radians. So my factor label method is going to tell me I want 1 revolution in the denominator so I can cancel that revolution. And then in the numerator, I'm going to have 2 pi radians. If I stopped right here, I would be calculating my angular speed. But I don't want to stop right there. I want to keep going. So now that I have angular speed, now I can go and convert to linear speed. Now when I think about going from angular speed to linear speed, I want to cancel the unit of radians. Okay? So now let's think about on this particular truck tire, the edge of the tire, 1 radian, when my angle changes 1 radian, how far, what kind of distance along the edge of the circle have I gone? Well, if it's 36 inches in diameter, that means my radius is 18 inches. So when my angle changes by 1 radian, I've covered the distance of 18 inches along the edge of my tire. Notice my radians cancel. And if I stopped right here, I would have the speed of my truck in inches per minute. But I don't want my answer in inches per minute. Now it's just a matter of unit conversions into miles an hour. So how about if we focus on the numerator right now? Let's get rid of inches. 12 inches are in 1 foot. And we want to get rid of feet, and we want that to be in miles. So 5,280 feet are in 1 mile. Cancel feet, cancel feet, cancel inches, cancel inches. This, if I stopped right now, this would be my speed in miles per minute. But I don't want miles per minute, I want miles per hour. So let's do that final conversion, canceling minutes. 60 minutes in 1 hour. So I've got minutes gone, and now if I look at my units are telling me, hey, you're ready to find the numeric part of your answer because I've got miles per hour. So now it's just a matter of doing some calculator work, and there's a couple of different ways you could go about doing this. Some people actually like to physically multiply every numerator, get that number on the top, multiply every denominator, put that number on the bottom, and then do the division. Some people are okay putting it in all at once. And let's see, I'm going to do 630 times 2 times pi times 18 times 60. Those are all in the numerator. And then I'm going to divide that by 12, and I'm going to divide that by 5,280, and I get 67.5 miles an hour. Pretty cool, huh? So that 36-inch diameter wheel going at 630 RPMs is going 67.5 miles per hour. Maybe you could even think about, well, what if I had a small car and the wheel was like a 24-inch wheel going at 630 RPMs? How would that affect my speed? Those are some things that we're going to do over the next few days, and I hope you have a great day. You can now work on either the arc length angle measure radius worksheet we handed out on Monday, or you can give a try to the circular motion problems that will be handed out today. Have a great day. I'll see you tomorrow.